Today we are going to study the constituents of polysaccharides. In this uh, lecture, we'll be discussing about the polysaccharides, what are polysaccharides, how we can elucidate the structure of a polysaccharide molecule. Let us start with what are polysaccharides. Now the important thing is what are polysaccharides. Actually, we already know about the monosaccharides, we already know about the disaccharides, and we know what are oligosaccharides and what are polysaccharides. So we say actually the polysaccharides are high molecular weight molecules which are having approximately 16,000 to 14 million atomic mass units. The molecular weight is approximate 16,000 to 14 million and are formed by repeated condensation of monosaccharides and oligosaccharides which are joined together by glycosidic linkage. So we already know that there is a linkage between the two monosaccharide molecules. For example, the glucose molecule, one glucose molecule is connected to other glucose molecule through a linkage, and that linkage is between a carbon oxygen carbon, and this linkage we call it as glycosidic linkage. They are connected with these glycosidic linkages, and based on their solubility we say that polysaccharides may be of three types. One, if they are soluble, completely soluble, water soluble, we call them as glycogens. Hydrolyzed by water and capable of gel formation, that is when we put them in water they can absorb water and they can form a gel that is an another form, and we say that amylopectin is an example of that molecules. And those that are completely insoluble in water, so we have a cellulose, and that is an example of the polysaccharides which are completely insoluble in water. Now we say that polysaccharides, they are generally having a formula C6H10O5 whole N, and when we hydrolyze them, that is we are adding water, the oil, this bond, that is glycosidic linkage, that glycosidic linkage is converted, that is cleaved, and we are getting the two new molecules, that is monosaccharide molecules. Or we can say in case of polysaccharides we will have monosaccharides, we will have different monosaccharides. There are some polysaccharides which may contain, in addition to the sugar, they may have some sugar molecules which are derivatives of sugar. For example, one of the hydroxy group of the sugar molecule has been taken, one of the sugar molecule has hydroxy group, that hydroxy group has been replaced by an amine NH2 group, so we call this an amino sugars. Or we have uronic sugars, for example we have actin example, where we can say that hydroxy group has been changed. Polysaccharides differ from each other. Now when we say that they are a composition, they are composed of many monosaccharide units, and we say they differ basically from each other in one, molecular weight, because they are having different molecular weight, you can say that different molecular weights. And then structural features, when we some say structural features, we say some of them are linear, for example amylose, and some others are highly branched, for example amylopectin. That means we may have a linkage, that is 1 1 6 1 4 1 3 1 2 linkages. They are linear molecules, and then there is another type of linkage which may arise because of 2 6 2 3 3 4. So they give us a branched structure, so we say they may be a linear, have a linear structure, or they may have a branched structure. Polysaccharides are connected with glycosidic bonds. Now when we say they differ, they also differ in the constitution of that or configuration of that glycosidic bond. So it may be either alpha, or it may be bond, the bond which is there, that bond may be either alpha, or it may be beta bond, that is that the the configuration of the bond between the two, that is glycosidic bond between the two monosaccharides, it can have an alpha linkage or it can have a beta linkage. And as I said that when we say the linear, they are usually having 1 2 1 3 1 4 or 1 6 type of linkages. That is, the glycosidic bond is formed between the carbon 1 and the carbon 2 of other monosaccharide unit. It may be the carbon 1 of one monosaccharide and one sugar molecule, and the carbon 3 of other sugar molecule. It may be between the carbon 1 and carbon 4 of the other, or it may be carbon 1 and carbon 6 of the other. So we say when it is a branched polymer, in case of we have, like I said, that it can be a 2 3, it can be a 2 6, it can be a 4 2, any combination which will give us a branch point, and the polymer is generated as a branched polymer. Now, based on this composition, we say that polymers, they are also known as polysaccharides, they are known as glycons. So, based on the composition, we say there are two types of polysaccharides. One is homopolysaccharide and another is heteropolysaccharide. When we say homopolysaccharides are having homoglycons, they are also known as homoglycons. And there are examples of cellulose, insulin, and styrene. For example, when we talk of cellulose, cellulose is basically made up of D-glucose, different molecular D-glucose. And if you take an example of the starch, again the starch is made up of D-glucose. Upon hydrolysis, it gives us the D-glucose, this monosaccharide units. Now, then what is the difference between starch and glucose? Definitely, it lies on the linkage, whether it is the alpha linkage or there is a beta linkage, and the combination of alpha or beta. So it depends on that. We say that these two molecules, though they are having the same monosaccharide unit, they differ from it. Similarly, there is an insulin molecule, and in insulin we have found that it is made up of fructose, D-fructose, and it has been found that this D-fructose, when it is in present in insulin, it is in the form of fructofuranose. That is, it is a five-membered ring. Then we come to the heteropolysaccharides. They are also known as heteroglycans. We have an example of alpha heparin. Alpha heparin is used as an anticoagulant agent. We have chondroitin sulfate A, and we have hyaluronic acid. So these are the examples which we say they represent different classes of uh, heteropolysaccharide. So it is essential to discuss the structure of polysaccharides. When we say that polysaccharide, how these polysaccharides have been, formed, and what is the constituent of these polysaccharides. In order to discuss the constitution of polysaccharides, we must know that what is the nature of monosaccharides present in these molecules. So when we say nature of monosaccharides, whether these monosaccharides, they are the constituent is basic building blocks of polysaccharide. So we should know that whether they contain the same polysaccharide, same monosaccharide, or they contain more than one type of monosaccharide molecules in them. When we say more than one saccharide, that is heteropolysaccharides, it has been found that they maximum there are 5 to 6 monosaccharide units present in the these heteropolysaccharides, and in monosaccharides there is only one. So it is the first thing that we should know about the constituent, that is the monosaccharide, which is important part of the polysaccharide. So we should have an information about which polysaccharides are present in the molecules. Then there is another one, that is ring size of monosaccharide. So it is also important to know what is the size of the ring, whether the ring they are present there, they are pyranose, that is in the pyranose form, that is a 6-membered rings, or they are furanose. As I said that in case of insulin, it is the furanose form of fructose ring that is present there. It is a 5-membered ring there. So in case of D-glucose, as I said, in case of starch, or in case of cellulose, it is the 6-membered pyranose ring. So it is also important to know the constituent of this ring, the size of the ring. So in addition to the to know the whether the monosaccharide units which are present, we should also have an idea that what is the ring which is present in whether it is a 5 member or a 6 member. Then come to the glycosidic linkages. The third part is glycosidic linkage. As I said that there are two types of linkages. Their linkage may be alpha or it may be beta. So it is essential to know whether the linkage which is present in the polysaccharide unit, it is alpha linkage or it is beta linkage, or the molecule have a combination of alpha and beta linkages. So in order to know the structure, we also should know the glycosidic linkages which are present in these molecules. Then structure of polysaccharides. When we say structure, as I said that is a possibility of linear or linear chain, or there is the possibility of branched molecules. So we should know whether the molecule which is present there, it is a linear molecule or it is a branched molecule. So this, from this also we should know that whether if it is a linear molecule, then we may have, like I said, we have only 1 2, or 1 3, or we have 1 4, or we have 1 6 type of combination linkages which are present there. And if it is a branch, then we may have other linkages which may give us a branched structure. Then the another important factor which is required for knowing the structure is the molecular weight of a polymer. So we should know the molecular weight, and that molecular weight, because we say that the different molecules, the different polymers or different polysaccharides, when they differ each other, they differ in the molecular weight. So that means the number of monosaccharide units which are present actually, because the number of monosaccharide units is directly proportional to the molecular weight, and we can say that this gives us an idea of the polysaccharide, that polysaccharide, what is the polysaccharide and what is its molecular weight, that is essential to know. Then we say that when we to find all these structures, we say that there is a process, that is elucidation of the structure. So to know the nature of monosaccharides, the ring of monosaccharides, the ring size of monosaccharides, to know the glycosidic linkages, to structure of the polysaccharides, whether they are a linear or chained molecules, and to know the molecular weight of the polymer, we have different techniques which we use, and these techniques are used for the this elucidation of the structure of a molecule. So among these, we say the first one is acid hydrolysis. We are doing the hydrolysis. Then esterolysis. Esterolysis is again another form. Then we have enzyme hydrolysis. We have methylation. We have peroxide oxidation, periodic oxidation, that is also known as semi degradation. We have the molecular weight determination method, and then we have the modern analytic techniques which also help us to know the structure of a molecule. So in order to know the structure of the molecule, let us start from acid hydrolysis. Now we know that hydrolysis, when we are using the acid to hydrolyze a polysaccharide, that polysaccharide converts into monosaccharide. So for example, we are having a glycosidic linkage there. It is C C C. I'm sorry, this C may be in a ring form like this. I am not forming the ring, like there is a ring here, and there is again a ring here, and we will have, when we are doing the hydrolysis, what will happen, the bond will be cleaved and there will be the formation of two units. So each monoglycosidic linkage is hydrolyzed and we are getting the different monosaccharide units. So you can see like it will be formed like this. This is a ring, and here we are having a hydroxy group, and similarly this is a ring and we will have CO. That is how the monosaccharide units are formed. So these monosaccharides are then tried to know the structure of these monosaccharides, and in order to know the structure of these monosaccharides, we have different techniques, like we have paper chromatography, and when if we are using the paper chromatography, then after that we are spraying that to find the black color spot, and we are spraying that paper with ammoniacal silver nitrate, and we find that which of the polysaccharide this monosaccharide unit is present. Or we can use, for in case of reducing sugars, we can use color characteristics. For that we are using an dimethyl aniline chloride. So in case of reducing sugars, we are using this for spraying on that paper TLC, and we will get in the TLC plate, and then we will get that information with which of the monosaccharide units are present in this case. Then we have another techniques like we have JLC, we have TLC, and we have zone electrophoresis, from the basis of which we can say that which of the rings are present, which of the monosaccharide rings are present. Then the hydrolysis also give us an idea whether the rings which are present, they are five membered or they are six membered. Because if they are in the five member, like they are furanose form, so in case of furanose form, it is easily hydrolyzed, readily hydrolyzed. And if they are present in six membered forms, that is they are having a pyranose form, then they are not readily hydrolyzed. They are hydrolyzed, but it takes time. So the hydrolysis also give us the idea whether the ring is present, the present monosaccharide ring which is present in the polysaccharide, whether it is in the five membered ring, like as a case of insulin. If we are doing the insulin hydrolysis, that will be readily hydrolyzed to monosaccharide molecules to get the fructose defructose molecules. But if it is starch or other molecules, then it will take time. So because they are having the monosaccharide, that is glucose, as in the form of a pyranose ring. Then second is estrolysis, then followed by hydrolysis. So what we are doing? We are doing the estrolysis first. We are taking a polysaccharide. We are treating that polysaccharide with acetic anhydride, and we are getting an acylated molecule, OAC. This OAC, when followed by treatment with sulfuric acid, we are getting the monosaccharide. So again we say that there is actually the hydrolysis of the the glycosidic uh, linkages. So we are having a glycosidic linkage, and that linkage is hydrolyzed to get the monosaccharides. This form is actually useful for 1,6 linkages. So this process is usually used for the molecules which are having 1,6 linkage, because 1,6 linkages are readily attacked by the acetic anhydrides, and then when we are using sulfuric acid and doing the hydrolysis, they are easily cleaved, although they may act on the other types of linkages also. Then the third form, we know that there is enzyme hydrolysis. When we take the example of enzyme hydrolysis, you might be remembering that when we say maltose, maltose, in case of maltose, we have used the one enzyme, that is maltase. And we said that time that the maltase is having a character that it only affects on the glycosidic linkage. And if we are having, for example, we have a linkage there, if it is a one linkage there, this is a this is the anomeric carbon, and this is the carbon. So there is possibility that if we are using some other hydrolytic agent, hydrolysis agents, there may be possibility that there will be ring opening. But if we are using the enzymes, they have the specific character, and they are use specific reactions. So we can say that when we are using the enzyme, it never acts on this ring. So it may act only on the, if it is like this, that ring is like this, it won't act on this ring, it will only act on the glycosidic linkage. So this is the character of enzymes. And then due to their specific nature, sometimes we are using the enzymes, and we use a series of enzymes, because we know that now the enzymes are having characteristic that they act on specific reactions, specific bonds. So we are using a number of and series of enzymes to remove the sugar residues, one by one or one or more at the same. It may be like we will use the enzyme, there will be a loss of one sugar molecule, then we will character that sugar molecule, then monosaccharide unit. Or we may use a series together, and we may have removal of number of sugar molecules, but they always start from the reducing end of the polysaccharide. So you know that the reducing end is where we have a free anomeric carbon that is not linked, and that will convert into aldosis or ketonic when we ketosis structure, and that will be reduced. That will, when we are using the Fehling's solution or Benedict solution, that will be reduced. So this is the character of enzymatic enzyme hydrolysis. Then is another method, that is methylation. So what is the use of methylation, then why we are doing the methylation? Right, when methylation is simply, we are actually using the protection, we are protecting the hydroxy groups. So the number of hydroxy groups present there, they may be hydrolyzed, they may be oxidized, or they may be degraded. When we are using the methylating agents, they will be converted into OCH3, that is an ether linkage will be generated. So a number of methylating agents have been used. For example, methyl iodide in a base, or dimethyl sulfuric acid and sodium hydroxide have been used. And one method that is more fruitful and that has been found very interesting was that of Srivastava et al. And was developed in 1963. He simply used the methyl iodide in barium oxide and using the dimethyl sulfoxide as the solvent. Methyl iodide in barium oxide and using DMSO in solvent, and he heated the temperature at 20 degrees centigrade. So then we get the final product, that is methylation. So in or what is the use of that methylation? Then one, that it won't be degraded, the hydroxy groups will be protected. When the hydroxy groups are protected, and after that we are doing the hydrolysis, we are getting the only those hydroxy groups which are free, they which are linked actually. For example, we are having here, we have carbon, oxygen, carbon, and this carbon is having linkage, that may be carbon 1, and we may have another carbon that may be a bond between carbon 3. For example, this is a 5 member ring, and we will have like the same have 6 member ring. So when we are doing the methylation, we have a hydroxy group here, CH2O H. That OH will be converted into OCH3. Similarly, if we are having an hydroxy group here, it will be converted into OCH3. Similar will be with all hydroxy groups, and we may have here hydroxy group, like when hydroxy group is present, that hydroxy group will be converted into OCH3. When we do the hydrolysis, then we will have all the groups that are protected except the one which was the glycosidic linkage. So we will have the free hydroxy groups here, and these free hydroxy groups will show us that the bond was between carbon 1 and carbon 3. So yeah, carbon 1 and carbon 2. So we say that there was a linkage, and that linkage was between carbon 1 and carbon 2. So it gives us one idea of the linkage, where the linkage is present. So second is like how many hydroxy groups are present in the molecule. That also gives us an idea of the number of monosaccharide units which are present, because we when we do the methylation, then we use a number of methods to know the methyl groups which have been used. And for example, we can use the Zissel method. We use NMR to define the number of methoxy groups, or we use the Zissel's method to know how many of the hydroxy groups were how many of the methoxy groups were used for the production of the hydroxy group. So this also gives us an idea about the number of methoxy groups, the hydroxy groups which are present, and then the groups which are free, which are not methylated. We can get an idea that these groups were basically methylated. These groups were basically involved in the linkage. So that also gives us the information about the linkages. Now, another method to elucidate the structure that we are using for elucidation of the structure is periodic oxidation, that is CIMIT, also known as CIMIT degradation method. In this method, we are using uh, sodium periodic acid, NiO4. That sodium periodic acid or periodic acid is having the character that which we have the two hydroxy groups which are vicinal, that is they are present on the two carbons, adjacent carbons. These carbons, when treated with NiO4, that is periodic acid, they will be converted into an aldehydic groups, and there will be the loss of the cleavage of this linkage, the CC linkage that will be cleaved, and we will get the two aldehydic groups. So only the hydroxy groups which are vicinal, only they will be oxidized to the aldehydic group. And then what we are doing is that we are using the sodium borohydride, NaBH4, sodium borohydride, NaBH4. And when we are using the sodium borohydride, that sodium borohydride reduces those aldehyde groups which have been generated. They will be reduced back into an alcoholic group. So you can say that the group that was produced, that was an aldehyde group, that is reduced back to an aldehydic, the alcoholic group, the primary alcohol has been generated. Now, why we are using, we are oxidizing it, that oxidation, from the oxidation we get an idea which carbons have been cleaved, with hydroxy groups have been cleaved, because we are cleaving those which are present, the hydroxy group, the bond between the carbons which is present between the two hydroxy groups having adjacent hydroxy groups. Those carbons, they will be cleaved, and that will give us a different, that will give us a cleaved molecule, then like here. So you can say that the first, and then why we are using sodium borohydride, because when we are doing the final hydrolysis, acid hydrolysis, we don't want to lose the aldehyde group. We don't want to have any damage, any degradation of that aldehyde group. So we are protecting that aldehyde group, we are converting it back into an alcoholic group. So the whole reaction proceeds like this. If this is an 1-2 linkage, in this 1-2 linkage, we can say when we are treating it with sodium per iodic acid, we are having a group present on the carbon 3 and 4 here. The two hydroxy groups are present, they are present on the adjacent carbon, and that these two hydroxy groups will be converted into an aldehydic groups. You can say that this is in carbon 1, carbon 3 and carbon 4, they have been converted, and there is a cleavage of the bond that was between the carbon 3 and 4. Then when we are reducing it, we are using sodium borohydride, they will be further reduced, the two aldehyde groups will be reduced, they will produce the two primary alcoholic groups. And the final hydrolysis, when we are doing the hydrolysis, we will see that there will be the change, these linkages, these are the glycosidic linkages. This one is a glycosidic linkage, this is also a glycosidic linkage. These linkages will be converted, they will be delayed, there will be the loss of these linkages. So we will find that this will be converted into an OH and H. Similarly, this will be converted into an, and we will see that since the ring, this pyranose bond, that is the bond between this oxygen cyclic ether bond, that will also be cleaved, and we will get an hydrolyzed product. So when the molecule will cleave, it will cleave in this way that we will have CH2OH, CHOH, and CH2OH. Since we know that one of the linkages will be between the carbon, the main carbon one that will be through O pyranose form, and then it will be attached to the carbon 5. So we do not expect that there will be a bond. The linkage, that is glycosidic linkage, will be with carbon 5. So what we see that if there's a in this you can see that clearly there is a cleavage of the bond that was between C3 and C4. So this shows that the linkage was not present at carbon C3 or carbon C4. And linkage is also not present at carbon 5, as we know that that makes an pyranose ring. So it is not there. Then why is the linkage? So we say that the linkage is between carbon 1 and carbon 2. So the molecule, this molecule was having two linkages. One linkage was with carbon 1, that carbon 1 was linked with one on one monosaccharide molecule on one side, and its carbon 2 was attached with another monosaccharide linkage, monosaccharide group on the other side. So this was an 1-2 linkage here. And in this molecule we can say that we are getting two glycerol molecules, and these two glycerol molecules are only possible if the molecule is having 1-2 linkage, uh, 1-2 linkage, and the two hydroxy groups which are present adjacent, they are oxidized to the aldehyde groups and reduced, and that bond, that carbon 3-4 bond has been. If there was no cleavage in the carbon 3-4 bond, if there would be a cleavage between the carbon 1, you can say 2 and 3, then we would have seen that okay, the bond may be between at linkage maybe between carbon 1 and carbon 4. So in this case we can clearly say that there the two glycerol molecules have been generated, and the linkage is between carbon 1, there is a 1-2 type of linkage which is present in the molecules. Now, when we move with 1-3 type of linkage, in the 1-3 type of linkage, we can say that since there is no hydroxy groups which are on adjacent carbons, you can say that there is a hydroxy group at the carbon 2, there is no hydroxy group at the carbon 3 because that is linked. Then there is a hydroxy group at the carbon 4, and then there is a hydroxy group at the carbon 6. So no two adjacent carbons are bearing the hydroxy groups. When this molecule has been treated with sodium sodium periodic acid and sodium borohydride, there won't be any change in the molecule, and when hydrolyzed, this molecule will give us a molecule that there will be hydrolysis, and when there will be hydrolysis we will find that there is a clear molecule, that is glucose molecule, and we can say that no change, and the whole molecule have been obtained. There is no cleavage in the molecule, the cleavage does not break into two small groups. So we say that it is only possible because there is a 1-3 linkage. If there would have been 1-4 linkage, then we could have found that the two hydroxy groups are on adjacent carbons. But since there is no adjacent hydroxy groups present on two adjacent carbons, we say that there is no change in this molecule, and the molecule won't be divided into two new ones, and only what we are getting is a complete monosaccharide unit. So in this case we say that this is a 1-3 linkage. Now similar to the previous ones, if we say that 1-4 linkage, as I said that we have to look for the two adjacent hydroxy groups, the hydroxy group present on the two adjacent carbons. In this case, if we see that there is a hydroxy group at carbon 2 and hydroxy group at carbon 3, they are adjacent. When we are using periodic acid, we'll see that the carbon 2 and carbon 3 hydroxy group, they will be converted into an aldehyde groups, and there will be a cleavage of the bond between carbon 2 and carbon 3. So there is a clear cleavage, and when we are using sodium borohydride, these two will be converted into alcoholic groups followed by hydrolysis. When we do hydrolysis, since there is a clearly we can say that the carbon 2 and carbon 3 bond has been already cleaved. When the molecule cleaves into two small molecules, definitely one molecule is having only two carbons, and the another molecule will have four carbons. So we are getting two molecules with one having two carbon units and another with four carbon units in the molecule. that is clearly shows that a bond has been cleaved between the carbon 2 and carbon 3, which was between the carbon yeah, a bond has been cleaved between the carbon 2 and 3. So we can say that the linkage was not on carbon 2 or carbon 3. Linkage is also not on carbon 5 because carbon 5 is in pyranose ring. Then we say the linkage was between carbon 1 and carbon 4. So in this case, it is clear that from there we get an idea about the linkage, where the linkage is present or linkage is absent. Now, if in case of 1,6, again, if we say that there is a linkage between the carbon, that is 1 and carbon 6, carbon 1 and carbon 6, when carbon 1 and 1,6 are there, we can say that there are hydroxy groups which are present. You can say that these hydroxy groups, when they will be converted, one adjacent carbon, carbon 2, carbon 3 and carbon 4, they are having the adjacent hydroxy groups, and all of them when used, so per iodic acid will be used, they will be converted, they will be oxidized. When they will be oxidized, we say that this carbon 3, there will be a cleavage of one carbon that will come out in the form of a formic acid, HCOH. Then the carbon 2, it will be converted into an aldehyde group, CHO, and the carbon 4 again will be converted into an aldehyde group. So we say that the carbon 3, which came out in the form of an formic acid, when there is, we say that okay, there were not, we say that there were not two carbons which were having hydroxy groups, two adjacent carbons, but there were three adjacent carbons, and among the three adjacent carbons, the central carbon came in the form of an formic acid. Then when treated with sodium borohydride, these aldehyde groups will be converted into alcoholic groups, and then final hydrolysis. On hydrolysis, we can say that now we are having one 2 carbon unit molecule and a 3 carbon unit molecule. So out of the 6 carbon units, we will say that there is loss of one already, one carbon unit in the form of formic acid, and the remaining one is glycerol and glycoaldehyde, that will come in the form of glycoaldehyde and glycerol. So we are getting a new linkage that we say that is an 1,6 linkage. So sim degradation, where we can say that we are degrading the molecule. From one molecule we are getting two components, and in case of 1,3 linkage we are getting the same component, and based on the components, the two components we are obtaining, we can give the products, where we can give the idea of the linkage, which linkage is present and which linkage is absent. Then the last one is molecular weight calculations. Now we say that molecular weight is an important criteria, and based on the molecular weight we can say the character of a polymer. And in this case we say that polysaccharides, they are also polymers of high molecular weight. So we need to know the molecular weight of that molecule, and on the basis of molecular weight we can get an idea that how many of the monosaccharide units are present in it, and what is the nature of that molecule. Now when we say that molecular weight, there are various methods to know the molecular weight of a substance. For example, we can use the viscosity, we can use the osmotic pressure, we can use the diffusion, electrophoresis, and X-ray analysis. And two types of molecular weights have been found. One is the molecular weight we say Mn, that is number average molecular weight, and one is Mw, that is weight average molecular weight. So when we say Mn is the number average molecular weight, and is defined as a weight of the sample divided by total number of molecules which were present in the mixture. So we will say the total weight of the sample divided by the number of molecules which were present, the number of monosaccharide units which are present in that, and then we say N1 M1 plus N2 M2, so on, divided by N1 plus N2, and we will get the summation of NIM, and summation divided by summation of Ni, and the basis of this we will get the total molecular weight, that will be number average molecular weight, where we can say that M1 is the number, N1 is the number of molecules having molecular weight M1, and N2 is the number of molecules having molecular weight M2. So we are doing the total number of molecular weight. Suppose we are having 230 molecular weight, and then we are having 5 molecules which are having that weight. We say that the 5 into 230 plus then there are 10 molecules which are having the molecular weight of 235. So we will say 235 into 10 divide by total number of molecules, that will be 10, and 10 plus 5. So we say that will be the total, and this will give us the number average molecular weight. Then the second one is weight average molecular weight. When we say weight average molecular weight, in that case we will say that the average of the molecular weights. In this case we have like mw is equal to summation of ni, and definitely when we say n is the number of molecules having same, n is the number of molecules having m molecular weight, and n2 is the number of molecules having m2 molecular weight. So when we do the summation of those, we say n1 m1 square of the molecules, and n2 m2 square, and we are adding those molecules, divide by, we say the total number of molecules and the total weight of the molecules, mi, the total weight of the molecules, that is the weight of m1, m2, m3. So we will say the total weight of molecules, and that will give us an average molecular weight of the molecule. Now, the main reason is like when we say that the two molecular weights, we are counting the mn and mw. Mn, if mn is same to m2, we say the molecule, so mn is same to mw, we say the molecule is homogeneous. And for heterogeneous polysaccharides, mn is always greater than mw. So this is one way where when we calculate the two molecular weights, we will have an idea that whether the molecule is homogeneous, the polysaccharide is homogeneous, or it is in heterogeneous polysaccharide. If mn is equal to mw, we say that both are equal, then we say they are homogeneous, and if they are different, then we say they are not homogeneous. Then osmotic pressure. Now there are various ways to calculate the mn and mw. For example, osmotic pressure, which is in colligative property, it is used to calculate the number average molecular weight. And viscosity, sedimentation rate, and sedimentary equilibrium yields mw values. Mw, that is weight average molecular value, molecular weight average molecular weight. So we can calculate using two different techniques. We can use mn, the osmotic pressure technique, to calculate mn. Then we can use the viscosity or sedimentation or the other method to calculate the mw. And if we find that mn and mw are same, we say that the molecule is homogeneous polysaccharide. And if these are different, then we say that molecule is not homogeneous polysaccharide, it is an heterogeneous polysaccharide. Then we will try to find it. Maybe we will use the hydrolysis by enzymes, so that we can get one monosaccharide unit at a time, and will identify that particular. And if we say that it is an homogeneous, then we can use any type of this hydrolysis, so that we know that any of the molecules which will be there formed, that is an homogeneous, that is the constituent of the whole polysaccharide. Then another method, that is now modern days, we have a number of techniques available which can be used. That is again the modern analytical methods. We have GLC, TLC, and zone electrophoresis. They can be used to identify the monosaccharides. Once we, after hydrolysis, if we get the monosaccharide units, and we can use those techniques to identify which monosaccharide is present and which is not, or the nature of the monosaccharide. Then we have ORD studies, and crystal studies, or monochromatic optical rotations, and from these we can get the information of whether the molecule is having alpha linkage or the molecule is having beta linkage. Another is NMR. We can use NMR for calculating that methyl groups. When we are using the methylation technique, we are methylating the polysaccharides, and we are getting methylated groups. So how many number of methyl groups are there, that can be obtained from using the NMR data, that can be easily used. And then IR is used to determine the nature of groups, such as carboxyl groups are there, estamide group, if estamide groups are present or not. So it gives us the information about the number of different groups which are present in the polysaccharide, and it also provides us the information about alpha or beta. configuration of the molecule. So read it as alpha or beta, not A or B. It gives us an information about alpha or beta type of linkages which are present in the molecule. So with this, we have concluded how the way we can know the constituent of a polysaccharide molecule, and we'll be taking some examples for that. Thank you.